Hello, Ramesh here. So now we will take the final approach to my favorite integral. That is the following. I equals the integral from 0 to infinity of e to the minus x square over 1 plus x square dx. Yeah? So we will expand this factor 1 over 1 plus x squared by first partial fraction decomposition as 1 over 2a times 1 over x minus I minus 1 over x plus I. Yeah? So our integral I will be 1 over 2a times I1 minus I2, the minus sign coming from here, of where I1 equals the integral from 0 to infinity of e to the minus x squared over x minus I dx, and I2 equals the integral from 0 to infinity of e to the minus x squared over x plus I dx. Yeah? So we will now tackle this integral I1 in the complex plane. Yeah? So we will consider the following integral IC, complex integral over some path, integral over a path C of e to the minus c squared over c minus I dc. Yeah? And we notice that this integral has a pole and at c equals I. Yeah? So we will use that in our integration path. So this is the real axis, this is the imaginary axis. So here will be the pole I, and the integration path will be over the real axis, C1, first path, up to the value of real equals R, then going up to R plus I, then going back up to epsilon plus I, then over a circle arc, yeah, and going down again through I epsilon plus epsilon till 0. Yeah? Minus I epsilon plus I. Yeah? So, okay, so let's do the integrals. Then we will name this path as C2, this one as C3, the arc as C4, and the final segment as C5. Yeah? Okay. So let's start with the integral over C1 equals integral from 0 to R of e to the minus x squared over x minus I dx. Yeah? So we are going just up to R. But we will take the limit as R goes to infinite. It will be this. It will be a better integral for our purposes. So, and this integral from 0 to infinity of e to the minus x squared over x minus I dx is just our original integral I1. Yeah? So, that's good. Let's continue. The integral on C2 is the integral on this segment here will be the integral from 0 to 1 of e to the minus R plus iy square over r plus iy minus I, and the derivative of r plus iy. Yeah. So this derivative will go to 0, and this integrand, we can see that we have an r here. The y is bounded, so it will the real part of r will dominate when the real part that is r will dominate as r goes to infinity, because we will get exponential of minus r times something. Also, we have an r in the denominator, so in the limit as r goes to infinity, this will go to 0. Yeah. So that's why we take limits as going to r going to infinity, because the integrals simplify. The integral on C3 will be the integral on this path here. So with the real parameter will be the integral on r to epsilon of e to the minus I plus x square over I plus x minus I dx. Yeah? So we can simplify this in the limit as r goes to infinity and epsilon goes to 0. Yeah, this integral will simplify to the following. We got an I because here we have an I, we got an E because we got the I in an exponent that will, when we expand the binomial, produce a minus 1 times a minus outside. So plus 1, e to the plus 1 is E. So then the integral from infinite to 0 of e to the minus x square minus 2ix over, here we simplify these i's, so x dx. Yeah. So this is the same as minus e integral from 0 to infinity of e to the minus x square minus 2ix over x dx. Yeah? So we will get another paper. Yeah. So then we are lacking our integral. We just made integral on C3. Now we will make the integral on the arc. Yeah. So we will plot again the arc here. So we have here the I is the pole. So the arc will be a circle segment. So this is C3, the arc is C4, C5. So then we will choose C equals epsilon times e to the I theta, where theta is a coordinate, angular coordinate in the usual polar coordinates, and epsilon is the radius, yeah, of the arc segment. So our integral on C4 will be integral from 0 to minus pi over 2, yeah, because it's going in this direction, of e to the minus I plus epsilon times e to the I theta square over I plus epsilon e to the I theta minus I times the derivative of c. And the derivative of c is I epsilon e to the I theta d theta, the differential. Yeah? So, then we can cancel the i's. Yeah? The epsilon e to the I theta will also simplify. Yeah? So, we will get I on C4 equals the integral from 0 to minus pi over 2 of e to the minus I plus epsilon times e to the I theta square times I d theta. Yeah? And as we take the limit of epsilon going to 0, yeah, we got that this is I times the integral from 0 to minus pi over 2 e to the minus I square d theta. Yeah? And this is just minus I e pi over 2. Yeah? Wow! We advanced a lot. And the final integral is on the segment. This segment. So, I sub c5 equals, then we take again a real parameter goes from 1 minus epsilon down to 0 e to the minus I plus iy square over I plus iy minus I. Oh, sorry, not plus I, it's just over the imaginary axis times the I dy, the derivative of this parametrization. Yeah? So, we simplify the i's. Yeah, and this is in the limit of epsilon going to 0, the integral from 1 to 0 of e to the I square over I minus 1 dy. Yeah? Sorry, y, not I here. The same minus integral from 0 to 1 of e to the y square over y minus 1 dy. Yeah? So finally, we calculated all the integrals. So this integral, yeah. Here also. Then we can use the following thing. So as we have avoided the pole, yeah, this pole, we left it out of the integral, of the path of the integration. So the sum of all these integrals, or the same IC, equals 0. So integral on C1 plus integral on C2 plus integral on C3 plus integral on C4 plus integral on C5, yeah, is 0. So from here we can get the integral on C1 as a function of all the other integrals, yeah. So integral on C1 equals minus integral on C2 minus integral on C3 minus integral on C4 minus integral on C5. Yeah? So we will write that in the next page. Then the integral on C1 then will be, and the limit that epsilon goes to 0 and r goes to infinity will be the minus the integral on C2. So minus integral on C2. but minus the integral on C2, we found here that was 0. Yeah? So, this is minus 0. Yeah? Then, minus integral on C3. Minus integral on C3 was this. Minus e integral from 0 to infinity of this function. So minus times this minus is plus e times integral from 0 to infinity of e to the minus x square minus 2ix over x dx. Yeah? Then minus the integral on C4. The integral on C4 is here, is minus e pi over 2. So minus times minus is plus. So plus I e pi over 2. Yeah? And finally minus the integral on C4. The integral on on C5. C5 here, not C4. C5. The integral on C5 is this one. So minus times minus is plus integral from 0 to 1 of e to the y square over y minus 1 dy. Yeah? And this is I1 equal to this. So e times integral from 0 to infinity e to the minus x square minus 2x I over x dx plus I e pi over 2 plus the integral from 0 to 1 of e to the I square over I minus 1 y minus 1 dy. Yeah? So we have expressed our origin, our integral e sub 1, I sub 1 as a function of these other two integrals and this constant. So then it remains to calculate I2. Yeah, let's remember I2 was the integral from 0 to infinity of e to the minus x square over x plus I dx. So for this integral we will consider now the fact that it has a pole and c equals minus I of the function e to the minus c square over c plus I dc. Yeah, the pole is in c is minus I. So if we calculate this new integral over a different path, we can again get this integral I2 over the real axis. Yeah. So for this integral we will consider the following path. So now the pole is in minus I. Yeah. So this is real. It's imaginary. Yeah. So the pole is here. So we will consider the following path. We'll go and we'll make an arc around the pole. So we will exclude the pole from the integration boundaries. Yeah. So we will go up to r minus I, then up down to the real axis, then going back through the real axis to the origin, and then closing the path. Yeah. So this will be C1, C2, C3, C4, and C5. Yeah. So again, as the pole is located outside of the integration path boundaries, then the sum of all the integrals of this complex integrand will be 0. So we will be able to get the integral on C3 as a function of minus the integral on C1 minus the integral on C2 minus the integral on C4 minus the integral on C5. Yeah? So, if we do that, we repeat the same procedure. We can do it, but we will not do it. It's the same. So we can do it. You can do it at home. Then you get the following. The integral, the I2 integral, in the limit when epsilon again, where epsilon is the radius of this arc, and this r and r is this coordinate, and the limit epsilon going to 0 and r going to infinity will be I2 will be e times the integral from 0 to infinity of e to the minus x squared plus 2xi. So this is the difference here. The sign here was negative, now we got positive in this exponent over x dx. We also get another sign in this constant here, minus I e pi over 2, and this integral will also get it, but with the same sign, plus integral from 0 to 1 of e to the y squared over y minus 1 dy. Yeah? So, when we make the difference of both I1 minus I2, we will get the following. So, you remember our objective integral was I equals 1 over 2i times I1 minus I2. Yeah? So, I equals 1 over 2i times I1 equals e integral from 0 to infinity of e to the minus x squared minus 2xi over x dx plus I e pi over 2 plus the integral from 0 to 1 of e to the y squared over y minus 1 dy, yeah, minus I2. I2 will be, yeah, plus minus e integral 0 to infinity of e to the minus x squared plus 2x I over x dx. So then we got minus, then we got another minus sign here, so it will be plus I e pi over 2, and then minus integral from 0 to 1 of e to the y squared over y minus 1 dy. Yeah? So we see that these integrals get cancelled, yeah, and this will add to remain there as we will add them, and divide by 2i will be e pi over 2, and then these other two integrals we will subtract them, and then we can see that we can factor the e to the minus x squared, and then we'll got the exponential of 2xi in both, but with different signs and subtracted. So we will get a sine function, yeah, minus e integral from 0 to infinity of e to the minus x squared over x sine of 2x dx. Yeah? Okay, so in a previous video we calculated the following, that the integral from 0 to infinity of e to the minus x squared over x sine of ax dx equals pi over 2 ERF of a over 2. Yeah, the error function. So, in this case, we see that the a in this definition here will be equals to 2. So, a equals 2. So finally, we got that I equals e pi over 2 minus e times this function here, pi over 2 ERF of a, that is 2 over 2 is 1, ERF of 1. So I equals e pi over 2, we factor 1 minus ERF of 1. Yeah, and this is just the complementary error function. Yeah, e pi over 2 times the complementary error function of 1. Yeah, and that's it. Okay, thanks for watching. I hope you like it. Bye.